Therefore, it converges to A over 1 minus R. A over 1 minus a tenth. A lot of sleepy people in here today, huh? Y'all are making me tired. Y'all are yawning and... Seven over 1,000. The bottom is what? 9/10. All right, flip it. 7 over 1,000 times 10 over 9. So cancel. I can just cancel 1 0 there. So you get 7 over what? 900? Is that right? 7 over 900. So if you were able to add those up forever, it would converge to this.
Does geometric ever diverge or not?
Yes, geometric can diverge. Just when you go to check this number R. I mean, let me show you a real quick one of a divergent. It's something like this, like 5 plus 5 times 2 plus 5 times 4 plus 5 times 8 plus 5 times 16 plus, so what does that look like? This is sum, n equals 1 to infinity, 5 times 2 to the n minus 1. See how these are all powers of 2? That's 2 to the first power, 2 squared, 2 cubed, 2 to the fourth. But it's kind of obvious that this is going to diverge, right? Like take 5, add 10, add 20, add 40, add, right? It's going to blow up. Pardon? They're pretty obvious. I think the book in one of the homework problems, they give you something that's a little tricky. You have to kind of mess with it a little bit. But all right, let me give you a different form. So far, the examples I've given you, I actually wrote the series out for you, and then we came up with the formula, right? Now what I'm going to do is I'm going to give you the formula and just ask you to figure out what happens to this. So how about sum n equals 1 to infinity of sorry, 5 to the n plus 2 over 7 to the n minus 2. Now you have to look at this and realize we're talking about a geometric series. And the thing that's going to make you think geometric is the fact that the index n is appearing in the exponent. And the geometric series always have to have an r to the n, right? So you have to have an n up in an exponent. So you start thinking geometric here. So your goal is to try and turn it into this. Can you convert this to this? Well, I have actually two problems, don't I? First problem is that my 5 is raised to the n plus 2. I need it to be n minus 1. And the denominator, 7, is raised to the n minus 2. I need it to be n minus 1. So I'm just going to do some algebra here, using the hidden zeros again. But I'm going to do it without actually writing them in. Let's just see if we can logically think of what we would need here. If this is 5 to the n minus 1 times 5, what would the power on that 5 have to be to give me back 5 to the n plus 2? 3, right? Cubed? Because if I take n minus 1 and I add 3, I would get n plus 2. Make sense? Next one. 7. I need n minus 1, don't I? Here, 7. Negative 1. You need a negative 1 on the 7. Because when I add them together, I need to be able to take n minus 1 and add to it something, negative 1. That when you put those together, you get n minus 2, don't you? Y'all see this? Okay. Yeah?
You just moved it over.
What's that?
I said, why did you feel like you were talking?
Yeah, I feel like I'm just talking to myself right now, actually.
You just moved the 7 to the top right.
Yeah, so everything that has the n minus 1 on it now, I can work with and hopefully get it to be something to do with my r. Everything else is just a constant.
So do you just put it to the front, like in?
Not out here. We'll keep it in here so that it's our a, but we'll put it out here, yes. Uh-huh.
So you're going to have 5 7 to the n minus 1.
Yeah, so we're going to have sum n equals 1 to infinity, and then 5 cubed is 125 times 7. Now here's my advice to you. Don't figure out what these numbers are, and because of what you're going to do with it in a minute, all right? So look, I'm going to bring the 7 to the negative 1 up. So I'm going to have 7 to the positive 1, 5 cubed. Of course we could just get this on our calculator, right? But I'm just going to leave it. And then watch this. I have 5 sevenths to the n minus 1.
Is that your R and A?
That's my r and my a. So why could I do 5 sevenths? These are both raised to the same power, right? And because of that, you can use properties of exponents that if you take a fraction and raise it to a power, the power goes both to numerator and denominator. So look at this now, and you see that it's geometric?
Yeah.
Yeah? Geometric. What's a? 7 times 5 cubed. What's r? 5 sevenths. What's the absolute value of r? Well, less than 1. 5 sevenths is less than 1. This is going to converge. Therefore, converges to a. 7 times 5 cubed over 1 minus 5 sevenths. Right? What's 1 minus 5 sevenths? 2 sevenths. So 7 times 5 cubed over 2 sevenths. Out of room. So if you need to write this as a fraction, you can. 7 times 5 thirds over 1, right? That's the numerator. I'm dividing it by 2 sevenths, which is the same as multiplying by the reciprocal 7 halves. I guess nothing is going to cancel. Normally on these, you'll get things to cancel, and that's why I like to leave them as 7 and 5, because like if this 7 had been down here, they would have canceled out. But these are just all numbers, right? So it doesn't matter if we write them out, multiplied out or not.
3,062.5.
What is it?
3,062.5.
Wait, something. Oh yeah, those are prime. Never mind. I was like, wait a minute, we're going to divide by 2. So what's 7 times 5 cubed times 7? Wait, what?
6125.
6125? And then all over 2. Something seems off. But, we just double check everything. Something seems off to me here. Both 7s. What are you talking about? 1 minus 5 sevenths. Say again?
I think he was saying you could just combine the sevenths and write it as squared, but it's the same thing.
Yeah, you could.
It doesn't change anything that much.
Okay. I'm going to trust it. The reason why I don't like that is because our answer is a finite decimal. Right? Like if you do it as a decimal, it's something 0.5. Right? Here? Flip.
No. He was asking
Oh.
what happened to the negative 1, and I was saying we flipped it up.
On that 7, it came up to the top. Okay. Trust the math. Trust the math.
Is that usually not happening or goes to the
It doesn't always happen. That's why I was a little concerned about it, but I made up the problem, so it could have happened. I just made it up, yeah. Okay, so let's take a look at something a little different. Actually, it's going to look very different. Let's say I give you this decimal right here, 0.185. And I ask you to convert it to a fraction. Do you all know how to convert decimals to fractions? Do them on the calculator. Exactly. There's a button, right? But how do you do it for real, like without? You count what place this is. This is tenths. This is hundredths, right? This is your thousandth place. And so really this is saying 185 1,000ths. That's what that is. And if you get on your calculator and type that in, you're going to get 0.185, right? Okay. You could reduce that fraction too, right? 5 goes into both, but that's how you convert a decimal to a fraction. But we're not going to do that. That's too easy, right? That's not why we're here. Here's what I want you to do instead. I want you to take the repeating decimal, 0.185 repeated. So 0.185 times, or sorry, 0.185, 185, 185, 185. Repeat that pattern forever. I want you to turn that into a fraction. And again, you could use your calculator for this? Is there a way to tell your calculator you want to repeat forever? I don't think there is. Yeah, so, okay. This is somehow connected to geometric series. Somehow. So let's start working with this. 0.185 repeated is 0.185, 185, 185, 185. Now if I wanted to, I could rewrite it this way. 0.185 plus 0.000185 plus 0.000000185 plus 0.00000000185. Do you agree that's the same thing? Okay, what is this first one written as a fraction? This is 185 over 1,000, right? Now be careful on this next one. What is the next one written as a fraction? It's 185 over, what place value are you in there? We're in the tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths. So 1 with 6 zeros. Plus, next one, 185 over, what place value are we in here? So 1 with 9 zeros. Understand? The next one would have 12 zeros, but I'm not going to write it. Pardon? Well, these are, would you agree that these are all powers of 10? Are these all powers of 10? Yeah, so maybe we can help ourselves by just rewriting it that way. 185 over 10 cubed plus 185 over 10 to the 6th plus 185 over 10 to the 9th plus dot, dot, dot. You starting to pick up on the pattern here? I could rewrite this in sigma notation. I know 185 is never going to change. I'm going to have 10 to some powers. I need to start out at 3, then go to 6, then go to 9. Those are all multiples of 3. So what should I put up here? 3n. 3n. If n is 1, what do I get? 3. If n is 2, 6. 3, 9. 4, 12. You see that? There it is. Doesn't have the n minus 1. In fact, it has a 3n, which is even worse, right? I need an n minus 1, and that's it. But I'm going to massage this thing. until I make it look like an n minus 1. So I'm about to use some properties of exponents. See if you can follow this here. We've got sum n equals 1 to infinity. 185 is just going to be sitting here times 1/10 to the 3n. All I did there was just, broke it apart and wrote it as 1/10 instead of 10 on the bottom. Then sum n equals 1 to infinity, 185. Now watch this. 1/10 cubed to the n. So we have properties of exponents. X to the n to the m is x to the n times m, right? So when you have two things being multiplied up here in the exponent, it's the same as doing that to a power to a power. So I took my 1/10 cubed, then to the n. Do you agree that this is still 1/10 to the 3n? Okay, but what's 1/10 cubed? 1/1000th, isn't it? 1/1000th. So I have sum n equals 1 to infinity, 185, and then 1/1000th to the n. What I've done is gotten rid of the 3. Do you see that? The 3 is actually gone here. And I need it to be n minus 1. So I'm going to do my little hidden 0 now. So who wants to tell me what my next line can be here? 185 what? 1 over 1,000 to the n minus 1, and then 1 over 1,000 to the just 1, right? So 1 here, I don't need the 1, right? So if I put these back together, right, I'm just going to get this. I've got the n minus 1.
So your A is 185 over.
185 over 1,000 is about to be my A. Sum n equals 1 to infinity. I've got 185 over 1,000, and then I've got my 1 over 1,000 to the n minus 1. Check, I've got geometric now. Got the formula, I can identify A and R. What's A? 185 over 1,000. What's R? 1/1000. That's smaller than 1. It converges. So this is going to converge to. So geometric A is 185 over 1,000. R is 1/1000th. Therefore, converges to 185 over 1,000 over 1 minus 1/1000th. What is 1 minus 1/1000th? 999 over 1,000. And then if you flip it, the thousands will cancel. And you get 185 over 999. So get on your calculator and type in 185 over 999. And I bet you you'll get 0.185, 185, 185, 185, 185. It actually turns out to be kind of boring because, like, this is the way it actually turns out. It really is kind of boring after you see it. But like, if you wanted to do like 0.45 repeated, what's your gut instinct as to what it's going to be? 45 over 99.
Can we do that?
No, you can't do that. But
It's however many numbers you have, right?
yeah, so if you had like 0.3257, then that's 3257 over 9,999. In fact, check this one out. This will kind of blow your mind a little bit. Check this out. What about the repeating decimal 0.333 forever? What about 0.333 forever? According to this pattern, this is the same as 0.3 forever, right? So according to the pattern, this should be 3 over what? 9, which is a third. That's right? If you did like 0.5 forever, that's going to be 5/9. So like I said, it's kind of boring after you understand the pattern. So as a take-home bonus problem, to show you that we can still do some stuff that's more interesting. This would be due next class. What's the difference? 0.00, then 581, 581, 581, 581. That is not going to be, your instinct right now might be to do what? Okay, 9's on the bottom, but how many of them?